Okay, hi everybody. My name is Kevin Ayala. I've been working with Jared Moore and Anthony Clark on a pipeline to design better simulated robots. And this talk is focusing on the work that we've done to improve the neural network component of that by pre-training with kinematic-based gaits. So I'll give you a bit of context about what that means. These are our animats. They're simulated robots. By our convention, they all have 4 legs and they have a neural network controller. And before any of this work started, they were all allowed to evolve sort of freely as long as they met certain objectives. But you can see that these sort of shapes that we create aren't very realistic looking. They're going to be harder to implement in real life. And so we wanted to see what we could do to improve that. So our previous work focused on just building this pipeline. The way it works normally is we have several different treatments that create different sort of brains and morphologies. And sometimes we start it with random body configurations. Then we allow them to evolve with these certain objectives like distance traveled, stability, and power efficiency. To start improving the neural networks, we started experimenting with pre-training. So in machine learning, pre-training is when you train a neural network on a subtask or sub data set in order to improve the overall task accuracy. And in this case, we started working with just random joint inputs and zeros and saw that it was already performing better than no pre-training at all. And when we got to training with feedback, it performed significantly better. Feedback is when we put in the output of the last node, rather the last step, as the input to the next node, so that our neural network would predict the next step based on the last step. And to get to the motivation of how we got to our question, which is pre-training with biological gaits, we had a couple of different goals that we were competing with. So the very first one is we wanted to prevent animats from gaming our system. Here on the right, you can see Jiggle Gait. It's a collection of images that shows a very common pattern that evolves with our animats, which is where they just start vibrating sort of violently and don't do very much of anything at all. It's not a very good gait, but because they can get some sort of movement out of it, they beat out their earlier competitors. And this is what we end up with instead of a regular walking gait or a regular moving motion. So we wanted to see if we could steer away from this sort of work. And then we started thinking, what if instead of steering away from something, we steered towards something? So what sort of information can we give it to make it better instead of just not worse? And we thought also, we should do this and reduce training time because it takes forever to train our neural network. And the whole point of evolution is that we could try out a bunch of different possibilities at the same time. In order to do that, we needed to find some sort of shortcut or some sort of correct answer already existing. And we turned to biological gaits. In real life evolution, the problem of how to walk has already been solved. Animals are walking within a few moments of birth sometimes. So we thought, what if we could import this data set and somehow use biological gaits to train our neural networks better? The hope of all this, the hypothesis, is that pre-training results in individuals that perform better and can be trained more quickly. And better is a very nebulous term here. So what we want it to mean is that it reduces the reality gap. So our individuals are more lifelike and they're easier to implement in the real world. So our research focuses on the part of the pipeline that creates a neural network controller. And we started just by reading veterinarian papers and figuring out what real world morphology looks like. So we focused on dogs. We figured out what healthy joint angles look like for them, what healthy movements look like for them. And then we tried to model that mathematically. It's not just about adding line segments to make legs, though. We also have to figure out what sort of angle limits exist and what sort of movements are natural for them. Then we once we had this modeled, we created a program that could generate joint angles for each step that they're taking. And that created a corpus of data for us to train our neural networks with. After that, it was a matter of changing our simulation environment to match up what the neural network was expecting. So this is the first building block of that, generating joint angles. You can see on the far left here is our representation of what a dog's leg should look like. Each part of the leg is a line segment, and each point is a joint. The bottom joint is an effector, that's their foot. That's not hinged. So we had to design a step for them to use, and our definition of a step was just a series of locations. So you can see each of the black squares there represents one point that we want the leg to touch in order to make the classic up and down movement. After that, we used inverse kinematics to generate joint angles for each step. So the inverse kinematics algorithm works by going bottom up through all the joints. Starting at the ankle joint, it'll try to point the effector towards the first location, and it'll go as far as its hinge allows it to, and then stop. Once that's done, the next highest joint will go. So that would be the knee in this case, and it'll also try to move as far as possible to point towards that first location. Once we've iterated through all the joints, then we evaluate whether we're at the location, in which case we move on to the next one, or if we're not at that location, we iterate through again. And this time, because the higher joints have moved, we have more mobility in the lower joints. Finally, we took our step and we designed several gaits by coordinating those steps. So for example, we have the middle image here shows a GIF of a walking gait. Walking gait is characterized by one leg leaving the ground at a time and all four legs acting in unison. On the right, we have a canter gait. Canter is defined as two legs leaving the ground at the same time, and specifically two opposite legs, so front right and left rear. Once we had our corpus of data, it was time to pre-train the controllers and figure out what the neural network would look like. Each yellow dot here on the screen represents one joint. Each of those joints has 2 degrees of freedom, so the joints can move left and right and forward and backward. There are 3 joints per leg, 4 legs, so that makes 24 inputs. We also added touch sensors at the bottom. Those are the black dots that you see, and those are just binary inputs for whether or not we're touching the ground. Lastly, we added a sinusoidal signal. This is a bit more complicated, but the goal was to encourage a sort of oscillating movement so that we're not seeing just sort of a start, stop, reverse movement. Instead, we see a more continuous flow. And here's what our neural net actually looked like. So in the first layer, that first layer represents all the inputs for the current state of a system. That's the current last step that's been taken. And 24 of those inputs are just what we talked about before, joint angles. We also have, those are the 29 inputs that we just talked about before. In the output layer, though, we only have 24 outputs because the output represents the next step for the animat to take. And we only need to know the joint angles in that case, not the touch sensors or the oscillating signal. Then we go right back into the pipeline. So once we insert them into the evolutionary process, things are mostly the same. We still have a semi-random body configuration, and we still evaluate against the same objectives. The way we do that is by using lexicase selection. So lexicase selection is multi-objective, which allows us to train on performance, efficiency, and stability of our individuals. And it works by comparing each individual against a series of test cases, where each test case is one of these objectives, and those test cases are evaluated randomly in order. Any individuals that fail a test case are filtered out. And then we have evolution asterisk. It wasn't quite the same as our previous pipeline because we had to match up the morphology of our simulated models to what the controller was expecting. So we had to make sure that the angles were what the dog expected. And that meant biasing the starting morphology so that instead of like fully random quadrupeds that as long as they just had 4 legs were cool, now we had to make sure that the starting angles were exactly what they expected and the body wasn't too big or too small. We also limited the angle ranges in perpetuity so that even for further generations, they wouldn't be able to evolve the crazy sort of angle ranges that we had seen before. So no more 360-degree movements, no more legs splayed out. It was a lot more akin to what you might have expected of a dog. And here's what that actually looks like. So take a look at the video on the left. That's very early on in our pipeline, just kinematics, not pre-trained on a neural network yet. You can see it's actually a pretty faithful translation. And I'll show you on the right now what that looks like when we actually try to pre-train a neural network with it. Not quite as good. Unfortunately, we had some issues translating the kinematic-based gaits into a neural network, and I'll talk about that in a little bit. But thankfully, because we used evolution, we were still able to propagate that further, we ended up with something like this after many generations. So this was a lot more successful, and in comparison to the gates that you saw earlier, a lot more realistic looking, a lot easier to implement in the real world. Fortunately, that doesn't mean we're quite done yet. We did get a couple of successful individuals, but in the aggregate, we didn't get the results that we were expecting or hoping for. The blue line here is, the orange line there is with pre-training. So that's our new pipeline that we created. And we were hoping to see an earlier plateau of training time so that after a certain point, the results wouldn't really increase. And that's when we know that we've reached the peak of our evolution. That didn't quite happen. We were also hoping to see higher distance traveled in our fittest individuals, and we didn't see that either. We did learn a lot from this research, though, and we do have a good roadmap to sort of fix some of the issues that we've seen. And some of the main issues is that we're having trouble translating between these kinematic gaits and a neural network controller, and that our simulation isn't quite up to par to create realistic animats. So the very first thing that we want to do is help with the translation side of it. Previously, we've seen only walking gaits. I think we saw one canter gait in our simulations as well, but we want to introduce gallop and trot. Gallop and trot are two unique gaits in that they are focusing on synchronous movement of the front and rear legs. So front and rear move at the same time. That helps to create a sort of pinching movement, and it's a lot easier complexity-wise than walking and cantering, in where a lot of different legs are moving in different ways at the same time. So we hope that this reduced complexity helps us translate from kinematics into neural networks. We also want to compare different neural network architectures. We've been working with just a fully connected feed-forward model, where the last output layer is the next step, and the first layer is the current step. We want to compare against specifically recurrent neural networks. So in a recurrent neural network, the outputs of all the previous nodes are passed in as inputs to the next nodes. And that helps it sort of create a pattern, and it helps it develop a sort of memory for what happened before. We know that in our use case, the pattern and the flow of what's been happening is very important, so that it's really hard to distinguish what the next step should be if you don't remember what the last couple of steps that you took were. In the midterm, we'd like to add some changes to our simulation as well. So when we were first training our neural network controller, we did evaluate to make sure that it was matching up with what the kinematic gaits were. And you can see it did a pretty good job. But when we go to evolution, we actually don't enforce this at all. Evolution-wise, they're free to develop however way they want. We think that by adding an objective to remain true to the kinematic gaits that we've trained with, we should sort of force them along the correct solution that we think we found. And in the very long term, we'd like to make some changes to our simulation. So I'll show you this video on the left here, which is one of our walking gaits that we've developed, a very weird one, but it provides a good opportunity to look at the simulation environment. It's just flat all the way around. We're expecting our animats to sort of develop these very realistic gaits to work in the real world, but they're responding to an entirely different environment than the one that we want them to. So by adding things like terrain and obstacles and maybe differing gravities, we're hoping to create a more realistic environment. And that should help our kinematic gaits succeed where these sort of gaming gaits are currently winning. All right, thank you all for your time. I'm happy to answer any questions now.